All right, let me tell you something that's going to bother you. It should bother you. It bothered me for years, and frankly, it still bothers me a little bit. Why can't you go faster than light? Now, you've probably heard this before. Nothing can travel faster than the speed of light. Fine, but why? What's so special about 186,000 miles per second? Why not 200,000? Why not 1,000,000? Why is there a speed limit at all in this universe? See, when I was 16 years old, I asked myself a question that changed everything. I thought, what would it be like to ride alongside a beam of light? If I could run fast enough, catch up to it, what would I see? And that question, that seemingly innocent question, leads you down the most extraordinary rabbit hole. Because the answer isn't just, you can't catch light. The answer is that if you could catch light, the entire universe would stop making sense. Time would stop. Space would vanish. The laws of physics would collapse into nonsense. And that's what I want to show you today. Not with fancy mathematics, though, we'll need a little bit, but with pure thought. With what Einstein called Gedanken experiments, thought experiments. Because the speed limit isn't some arbitrary cosmic rule. It's baked into the fabric of reality itself. Let me show you the simplest possible clock. Take two mirrors, one on the floor, one on the ceiling, and bounce a pulse of light between them. Every time the light hits the bottom mirror, tick. Hits the top, tock. Tick, tock, tick, tock. Now, if those mirrors are 150,000 kilometers apart, that's about the distance light travels in half a second. Then your clock ticks once per second. Perfect, simple, beautiful. But here's where it gets interesting. Put that clock on a spaceship and send it flying past you at, say, half the speed of light. You're standing still, watching the spaceship go by. You can see the light pulse through the window. What does it look like to you? Well, to the person on the spaceship, nothing's changed. The light goes straight up and down, tick-tock, just like always. He's moving with the clock. So, from his perspective, everything's normal. But you standing on Earth, watching the ship zoom past, you see something different. You don't see the light going straight up and down. You see it going on a diagonal path. Because while the light pulse is traveling from floor to ceiling, the whole spaceship has moved forward. Now, here's the critical part, and this is where your intuition is going to rebel. The speed of light doesn't change. Think about that. The light pulse has to travel a longer distance, that diagonal path you're seeing, but it's still moving at exactly the same speed, 186,000 miles per second. Not 186,001, not 185,999, exactly the same. So if the light has to go further and it's going the same speed, it must take longer, which means the clock ticks slower from your perspective than it does from the spaceship's perspective. And that's not a quirk of the light clock. All clocks on that spaceship run slower. The astronaut's wristwatch, his heartbeat, the time it takes him to think a thought or light a cigar. Everything is slowed down by exactly the same factor. This isn't philosophy. This is what actually happens. We've measured it. Atomic clocks on airplanes, particles called muons, raining down from the upper atmosphere. GPS satellites that have to account for this effect, or they'd give you directions to the wrong place. Time itself runs slower when you're moving. Now, let's push this further. Let's say you want to catch up to light. You build a faster spaceship. You're now going 90% the speed of light. Close, right? You shine a flashlight forward. How fast does that light move away from you? Your gut says it should be going just 10% faster than you because you're already going 90% of light speed, so the light should only be pulling ahead at 10% of c. Wrong. Dead wrong. The light is still moving away from you at exactly 186,000 miles per second. Full speed. Not 10% faster than you. Not 20% faster. The full, complete, original speed of light. This is insane. How can this possibly work? Well, it works because when you sped up to 90% of light speed, several things happen to you. From the perspective of someone standing still, your spaceship got shorter, physically contracted in the direction you're moving. Your clock slowed down, time is passing slower for you. And your mass increased. You got heavier, much heavier. And here's the kicker. As you approach the speed of light, your mass approaches infinity, your length approaches zero, and time nearly stops. Now, what does it take to accelerate something? You need force, right? Force equals mass times acceleration. But if your mass is increasing as you go faster, you need more and more force to produce the same acceleration. And as you get closer and closer to the speed of light, your mass gets bigger and bigger, until at the speed of light itself, your mass would be infinite. To accelerate infinite mass requires infinite force, which doesn't exist. So you can't get there, ever. Not with all the rocket fuel in the universe, not with all the energy in all the stars. The speed of light isn't just a speed limit, it's an asymptote. You can get arbitrarily close, but you can never, ever reach it. Let me give you an example from nature that proves all this is real, not just theoretical nonsense. High in the atmosphere, about 10 kilometers up, cosmic rays smash into air molecules and create particles called muons. These muons are unstable, they decay. They fall apart after about 2.2 microseconds on average. That's 2.2 millionths of a second. Now, even if a muon is traveling at nearly the speed of light, in 2.2 microseconds, it can only travel about 600 meters, maybe 700 if you're generous. But we detect these muons down here, on the surface of the Earth, in laboratories. They're created 10 kilometers up, that's 10,000 meters, yet they reach us before they decay. How? Because they're moving so fast that time dilation kicks in. From our perspective, watching these muons zip toward Earth, their internal clocks are running incredibly slowly. What feels like 2.2 microseconds to the muon might be 20 or 30 microseconds to us. And that extra time allows them to reach the ground before they decay. We can measure this. We can look at muons of different speeds and verify that the faster ones live longer from our perspective. The formula works. The time dilation factor, 1 divided by the square root of 1 minus v squared, c squared, predicts exactly how much longer they survive. This isn't speculation. This is nature screaming at us. Time is relative. The speed of light is absolute. Wake up. Now, here's where the story gets historically fascinating. All of this, the constancy of the speed of light, the relativity of time, was hiding in plain sight in James Clerk Maxwell's equations of electromagnetism. Maxwell wrote down 4 equations in the 1,860 seconds that completely describe electricity, magnetism, and light. Beautiful equations, gorgeous. They unified 3 phenomena that people thought were separate. But here's the problem. These equations didn't obey Galilean relativity. In Galilean relativity, the old Newtonian way of thinking, if you're in a train moving at 50 miles per hour and you throw a ball forward at 20 miles per hour, someone on the ground sees the ball moving at 70 miles per hour. You just add the velocities. Simple. But Maxwell's equations said light doesn't work that way. If you're in a spaceship moving at half the speed of light and you shine a flashlight forward, Maxwell's equations predicted the light would still move at exactly c, not 1, 5c. This created a crisis. People thought, well, Maxwell's equations must be wrong. They're new, only 20 years old. We need to fix them so they obey Galilean relativity. But experiments kept failing. The Michelson-Morley experiment in 1887 tried to detect Earth's motion through the ether by measuring tiny differences in the speed of light. It found nothing. 0. The speed of light was the same in all directions, regardless of Earth's motion. People were confused. George Francis Fitzgerald even proposed that maybe objects physically shrink when they move, and that's why we can't detect the ether. He was half right. Length contraction is real, but not for the reason he thought. Then Einstein came along and said something radical. What if Maxwell's equations are right, and our assumptions about space and time are wrong? What if time isn't absolute? What if different observers can legitimately disagree about whether two events happen simultaneously? What if space and time are woven together into something more fundamental, space-time? And with that insight, everything clicked into place. Now, let's talk about what this means for space and time themselves. In Newtonian physics, space and time are separate. There's absolute space, like a fixed stage, and absolute time, a cosmic clock that ticks the same for everyone. But relativity destroys that picture. Space and time are mixed together. When you change your velocity, when you change how you're moving through space, you also change how you're moving through time. And there's a deep symmetry here. Just like rotating, your perspective changes. Which direction is north and which is east? Changing your velocity changes what you consider space and what you consider time. The mathematician Hermann Minkowski put it beautifully in 1908. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. We call that union space-time. It's a four-dimensional fabric where three dimensions are space and one dimension is time, but they're woven together in a way that makes them inseparable. And the speed of light? That's the conversion factor between space and time. It tells you how much space corresponds to how much time. A light second is a unit of distance about 186,000 miles. A light year is also a unit of distance. In natural units, the way physicists like to think about it, you can just set c equals 1. Then time and space have the same units. A second of time is also 186,000 miles of space. They're interchangeable. And in those units, the speed limit is just, you can't go faster than 1, because 1 is the speed that preserves the structure of space-time itself. So the next time someone tells you, nothing can go faster than light, don't just accept it. Ask why. Push on it. Think about it. Because the answer isn't because that's the rule. The answer is because if anything could, the universe would stop making sense. Cause wouldn't precede effect. Time wouldn't be time. Space wouldn't be space. Reality itself would collapse into nonsense. The speed of light is the speed at which the universe thinks. It's the maximum rate at which information, cause and effect can propagate. And that's not a limitation. It's a fundamental feature of how existence itself works. And that, my friends, is something worth understanding. Now, go think about it, and let it bother you the way it bothered me. Because that's how you really learn physics, not by memorizing formulas, but by letting the strangeness of reality collapse your mind, and then building it back up again, stranger and more beautiful than before.